Right. Well, hello, everyone. So, unfortunately, the lecture, when I recorded it during lecture, didn't work. The audio didn't work. So, I'm actually re recording this lecture for you guys that missed it. Um, basically, yeah, for those of you that are SFN or so for those of you that want to review the linear regression content, I'm going to actually just step through this content. Basically, this is just me on my computer. So this lecture actually wasn't too long, so hopefully, yeah, you guys can get something out of this. But yeah, so what we went over was linear regression as a topic. Um, I started out by sort of contrasting this philosophically, this approach with PCA, which we had gone over the week prior. And so basically, the idea being that when we did PCA, the whole idea was to look at the data alone and try to figure out the internal structure of that data. And during that lecture, I called that process an unsupervised learning procedure. And so that's probably the most popular unsupervised learning procedure. Today, I'm going to talk to you about linear regression, which is probably the most popular supervised learning procedure. It's sort of pretty simple to implement, but it works sort of structurally in a very different way. And I think I described this 2 weeks prior, but basically that the idea is that there's a training component and we're learning a model, and I'll sort of explain what that is as we sort of step through this, but you end up using data in a way to train a particular model and with sort of the stated goal to test the model later. And in particular, we think of this framework as working in a predictive fashion. So whereas PCA just the goal of PCA was to find sort of special axes that we sort of illustrated as useful possibly to reduce the dimensionality or reduce sort of the amount of data that some big data set may take up, or you might use those special axes to visualize the data in a particular way. Linear regression sort of structurally works in sort of a different way. And the goal is, in fact, to predict some sort of output, which we're going to call y, from sort of input x. In order to do that, we sort of train on xy initially, and then later we look at some inputs x and try to predict some outputs y. And that's sort of this framework. And so this is sort of what this first slide is basically attempting to outline. So just as a brief review of statistical learning, last time we talked about principal components analysis, which I described as, again, this unsupervised learning procedure. And we use this to find, again, a special basis. This was a special set of orthogonal axes that sort of aligned with our data in a particularly useful way. And we use that basis to sort of illustrate or to sort of view the data in a way that has a variety of advantages. But today we're not going to focus on that unsupervised learning procedure. Instead, we're going to focus on what I'm calling a supervised learning procedure. Again, this being today's focus. And we're going to do this in the context of linear regression, but in general, supervised learning procedures use data to find model parameters. And I'll sort of explain exactly what I mean by a model and exactly what I mean by parameters as we sort of go through. But basically, the stated goal of the supervised learning procedure is prediction. We want to predict some output y from some input x. I sort of have used this example of height and weight before in lecture many times. And so you can imagine this as predicting some type of, say, weight y from sort of input height. And you can imagine, of course, you cannot exactly map that well, but you can with some confidence predict that sort of output from that input. And you can do that through a variety of ways, but again, the way we're going to talk about is to fit a statistical model. And we're going to use some data to figure out what the shape and what the look of that model should basically be. And then once we have the model, you can provide me a height or a weight, and I can give you again, the output there. So that's sort of where we're going. So again, we're going to start out with a simple two-dimensional example. You can imagine here, so this is exactly what I'm talking about. I've gathered some data to begin with, and I have some, say you can imagine this x, which I'm calling my input, is height, and then, well, in this case, the axes don't align with that, but this can sort of be anything, and the output is some predictor that I'm trying to make. So again, we give some data, and our goal is to best predict y, our outputs, or our outcomes, given some input x. So how might we do this? Well, this is a bit of a challenging question. But one simple way to think about this question is to search for a function that maps y from x sort of as maybe as well as possible. And so how might you do that? Well, you could imagine connecting all of these little points and making an explicit function that just connects all of these points that I have outlined here in blue, and that would be some function that predicts y from x. But of course, that function's actually pretty hard to sort of write down if I actually do that, and that function's a particular feature of only the data we have. So that might not be a good goal. Instead, we might want to think of maybe what's some simple function that generally captures the trends we see in the data. So let's think of classes of functions that might generally capture the trend without maybe just focusing on every individual data point. I'll sort of explain in more detail what I mean by sort of generally capturing a trend, and sort of describing this in some sort of general way with some sort of noisy variation, as I'll sort of explain as I go through more. But again, the idea is just to try to figure out some kind of function that can predict, that's basically a function of x that gives some sort of output y. So it can be hard to sort of find any function to do this. Functions can be, of course, a variety of forms. They can be complicated in a variety of ways. So one of the ways as statisticians we sort of constrain this problem to make it solvable is to think of a class of possible functions that can, again, sort of map this output y from this input x. And the one we're going to focus on today is like, let's imagine just doing this. Well, so first, I guess you can see we could imagine having a function that all has this sort of curved upward shape. Maybe these are all look sort of like logarithmic based functions, or maybe we have some sort of line that fits the data, or maybe we imagine a curve the other direction. Maybe those are quadratic fits to the data. And you can sort of imagine that each one of those functions that I have outlined in each one of these colors sort of has a different form. And so one of the things we do as statistical modelers is try to figure out, well, how do I model this output y from this input x? And maybe I sort of select a class of functions to begin with to sort of constrain my problem. And in this case, we're going to be focusing on, of course, lines. This is a linear regression lecture. And we're going to be only considering functions that have this linear relationship. And you might imagine that that's simpler to learn, and that's because it in fact is. But I don't want to undersell this. Of course, linear regression is used in a variety of contexts and can be very, very powerful. And some of that comes from the fact that this is actually a simple class of functions that can be learned sort of quickly. And we'll sort of step through this in more detail. But of course, I do want to stress that picking the class of possible functions, or basically said differently, this is picking the statistical model that we are using to understand how to predict some data y from some inputs x is a really important decision. There's a lot of work that sort of goes into how do I choose a model, and how do I compare different types of models? If I fit these data with curvy purple lines or straight red lines, those are different statistical models. They will give me different approximate functions x that map functions f that map x to y, and there might be some advantages or disadvantages to each of those approaches. And actually comparing across those can be pretty challenging. There's a lot of work that goes into how you compare different types of models, and also even just picking one to begin with can sort of be a challenging decision. And often as statisticians, we don't have a particularly rigorous way to choose a model. Sometimes we do, and sort of that might depend on some features, but often we don't. Often we just sort of go with a class of models that we think might actually capture the features of the data. Maybe we just look at the data and we say, oh, this looks as if it could be captured perhaps with a linear relationship, or maybe we don't. Maybe we just plot the data down, use some class of functions, say I call them linear functions, that's my model, it's a linear model, and I see how well it does. And if it doesn't do well, maybe I pick something else. So, there's a bit of an art to this, but of course this first step can be super important sort of moving forward. If anyone starts using these sort of modeling procedures in the future, you have to be aware that sometimes the first step is to just pick a class of models. So of course today we're going to be using linear functions. This by this I mean our class of models is going to be a set of lines or planes or hyperplanes, and I'll go into that in a little more detail as to exactly what I mean. But yes, we're going to be dealing with models that are linear functions of x. So probably you guys are familiar with exactly what this is in a one-dimensional input and output case. Again, predicting heights from weights, for an example, or maybe predicting heights and weights is a good example. You probably know the formula for finding the best fit line. This is sort of taught at the high school level pretty regularly. I'm sure everyone's sort of seen it. The formula sort of rings true as this famous y equals mx plus b. And so we're going to start out here. You know that this is finding the best fit line of your data. This is linear regression. This is using a linear model to best predict y from x. And what I'm going to do now is just give you different terminology to sort of the language that I'm going to be using moving forward, talking about modeling and how we end up using this sort of from an implementation point of view. And yeah, so this is just going to be vocab. So and here's a figure, describing what a best fit line looks like for a single dimensional x input and y output. This was the same slide I had on before, and I'm just going to sort of give names to each of these pieces. And so in particular, you might already be familiar with this. Y we sometimes refer to as the dependent variable. We call that because it obviously depends on some sort of input x. It's also the thing we are trying to predict. Sometimes we call this the outcome or the response. And x you might already be familiar with as the independent variable. The two other terms for x that you may be less familiar with is what I might use today, is a regressor. We sometimes call x a regressor, and sometimes we call x a predictor. And I think more importantly, though, the other two parts of this model, m and b, are what I'm going to call model parameters. So again, to sort of say this differently, the goal of linear regression is to find a line by tuning these model parameters. So we seek out an m and we seek out a b that basically best predicts y from x, having trained on examples of y and x. So just to bring it back to the first slide, I said earlier that supervised learning procedures have a distinct training phase and testing phase. And this formula you're already likely familiar with is actually doing precisely the same thing. So you have initially some data, some pairs of x and y, some measurements of heights and weights, for example, and you seek to find a particular value of m and a particular value of b that best captures that relationship of your data. And why do you do that? You do that ultimately so you can test, so that later on, if I'm provided with some x, I can predict some output y with some confidence. And so that's sort of in the spirit of what we're doing, and just the titles here, we're calling M and B model parameters of a linear model in this case. And we learn the model parameters. Great, so I'm going to do a slight notation shift because mx plus b is sort of the high school way to think about this problem. I'm going to make a subtle change that isn't too big of a deal, but I'm going to change that m to a b1, and I'm going to change the b to a b0. And this will make more sense going forward as I sort of extend this model to a more general case, but we're going to call m and b b1 and b0. And so just said differently, this is the goal of this procedure is given some training data, x and y, we seek to find model parameters b0 and b1. Once they're found, we can test our model to see how close we can predict y given some value of some input x. Again, that's sort of the overarching goal in this single-dimensional x and y case where x and y are just scalars. Great, so we now want to think about this in a bit of a more rigorous way. So earlier I said, we're using these functions f of x, in this case linear functions, to describe y. But of course, the y is never perfectly described by x. You see that line, but it It doesn't actually capture all the data. And why is that? Well, that's because data are actually random and noisy. And so if I'm going to be rigorous and sort of introduce you guys at this point to what I mean when we're talking about statistical modeling, we need to be more precise with this process of randomness or noisiness. And in particular, the procedure we're doing today you can think of as a probabilistic linear model. And why is it probabilistic? It's probabilistic because that output y is never exactly a function of the input x, right? It's a function of the input x characterizing some sort of error, some sort of randomness or noisiness about some sort of expected or average value we might find. And so I just want to go through and make this part precise. Of course, the fact that these data are sort of random and sort of do only, an f of x can sort of capture a trend, but of course you can also fluctuate around this f of x according to some noise. Isn't a bug, but in fact it's a feature. And by that I mean in probabilistic linear modeling we know that data in fact do have some sort of randomness or noisiness associated with them. In neuroscience, of course, if I record from a neuron and present the same stimulus 10 times in a row, I will not get the same spike trains out 10 times in a row. And why is that? That's because, of course, the brain is noisy. The brain is random. So if I want to find some sort of trend to describe firing rates of neurons, I want to be able to capture that randomness and noise a little bit. And again, with the height and weight model, of course, your height does not exactly predict your weight, for example. Why is that? Well, this is because there is no precise relationship. This relationship does fluctuate. It is random and it is noisy, and this is the way sort of the natural world looks, and this is the way sort of data exists as we gather it. So in order to do proper statistical modeling, we're assuming that the natural world is sort of randomness, is random and noisy to some extent. So that's sort of, how we're outlining this. And so, in particular, all of the models that we choose when we're choosing, say, a given f of x for a model, we can think of it as having two parts. On one hand, it has this deterministic part, this line, and in another hand, it has some piece of it to characterize how probabilistic or how noisy the data are. And so another way to write the linear model, previous to this point, I have given you only equations for the best fit line. That was y equals b1x plus b0. I've appended here on the bottom of this slide this additional component. It says plus epsilon. And so what does this mean? Well, this epsilon feature is it's called a random variable. It actually captures the fact that y is not perfectly known from some input x. So the idea here being that the epsilon captures the fact that the real world data are noisy, right? So this epsilon is a probabilistic part of the model. Without this epsilon, we can only say something like y approximately equals b1x plus b0, but now that we include this epsilon, we basically are saying y equals b1x plus b0 plus some deviation, plus some random deviation, and that could be a slightly above the line that I've drawn as a best fit or slightly below the line I've drawn as a best fit. And so the claim we basically make here is that x is only related probabilistically as an outcome y to this model, and by writing it this way with this epsilon, and sometimes they say, you might see this if you're ever looking at in this, ever look up a linear model in a paper, you might see something like epsilon is coming from some sort of distribution, some sort of probability distribution. That's again because epsilon is what we call a random variable, and epsilon can sort of take on a range of values sort of in a stochastic or sort of random way. And one interesting thing to point out is you might imagine that the amplitude, or sort of how random epsilon can sort of change. If my linear model, if my x predicted my y very, very poorly, on average those epsilons would be very, very large values. So you might imagine that epsilon is drawn from a distribution that has a lot of choices. If my linear model is really, really good, That is, if x predicts y very, very closely, on average, epsilon has a very, very small value. And so, I've talked about in class ways to categorize sort of the range of things as probabilistically capturing their standard deviation. And so that applies here too. If if epsilon is drawn from a distribution with a large standard deviation, my y varies about my line on average quite a bit. And alternatively, if epsilon is drawn from a distribution with a very, very small standard deviation, it tends to achieve a value that's actually quite close to 0. So typically we say that the epsilon here's average is always 0, but it sometimes is above 0 and sometimes is below 0. So if that standard deviation is really, really small, those values will always be really, really small. And in that case, my y captures my x to a confident degree. And so again, just sort of big picture here, you're used to this formula, mx plus b, or b1x plus b0. And all I've done is appended this with an additional extra epsilon component, and I've called this the noisy part, the probabilistic part, the random part. And this epsilon can take on varying values and sort of how wide of a range of values it carries on as a reflection of how good this linear model fit is to the data y given the input data x. Great. So just stepping through this more concretely, I have here some example data plotted on a x versus y plot, and this data is highlighted here with these blue dots, and I have this best fit line drawn, and I've also shown a line here from the data to the best fit line. And you can think of these as the epsilons I showed in the model before. And for each data point, I've drawn a different epsilon. Again, epsilon was a random value. Epsilon could have taken a value above 0, as is the case in the fourth and first data points. It could take on values below 0, as is the case in the second and third data points. And the outputs here, given some input, say let's look at that first blue point all the way to the left, that has some value x, close to the left side of the axis, and some value y, and I've labeled that there as true y. And that's, again, the data. But of course, my best fit line is into that true y. It deviates from that true y by a certain amount, and in particular, that amount is epsilon, which is random, but for this one data point, it takes on a particular value. So again, that's exactly what is outlined here. So a given data point x predicts some data point y plus some epsilon, and that epsilon, if it's some positive value, say epsilon 1, that perfectly describes this lefternmost point on this plot. Great, and of course the line is some linear fit of that line with some learned parameters b1 and b0. Great. So, according to probabilistic linear models, we can make the following claim, that the average value of y is given by this regression line, y equals b1x plus b0, but an observed y can deviate from this regression line by some random amount that we're capturing in this epsilon. To learn this model, and so up until this point, I've basically talked about the best fit lines as if we already know them, but of course the goal of this supervised learning procedure is to find this line, is to find those parameters, and the way we find this parameter is to find a way to minimize this epsilon and thus maximize the predictive power of y given some sort of input x. So doing that means trying to find the line that minimizes the length of all of those red lines. Now, if we think back to the PCA lecture, our goal in finding that first principal component was distinctly different, but it was similar in some way, in that it was a procedure that attempted to minimize or maximize something. And in that case, the procedure was to project all these blue points onto this line and maximize how much they vary, right? That was a special axis that we found. In this case, I'm finding a different line. It's not really an axis of the data. Instead, it's a line that minimizes the vertical length of all of these points projected on this line. So again, said differently, to learn this model, we want to find the parameters, in this case b1 and b0, that minimize all these epsilons. They basically shrink the red in that plot as much as possible. That sort of shrink those lines, sort of the net length of all of those lines, to as low of a value as I possibly can. And by doing that, we found a line that captured this data pretty damn well, right? So it sort of is the best description of the data we possibly can. It minimizes how much of y is explained with the noise component and maximizes how much it is explained with the parameter component. So title for these guys, you might see this, well, you're likely to see this again if you're in data science in any capacity, but typically they'll call these residuals. And the goal of linear regression is to minimize the residuals, to find the parameters b1 and b0 that minimize the residuals and thus maximize the prediction of y, given some sort of input x. So everything I've said conceptually is now outlined in a pretty concrete and simple equation. I think I said this to you guys before in lecture. If we are not, of course, if my epsilon for when a point is below the line it's going to be the line minus the data point. That distance would be negative. If my data point is above the line, the data point minus the line would be positive. So in order to ignore the fact that these guys are either positive or negative, we square them. So sorry, let me say that again one more time. If we look at the formula at the bottom of the page, we have a function of our data. And say we have one data point. Well, one data point has one value x and one value y. So let's say I equals 1. It's the first data point. Well, I want to plug in that value x and plug in that value y. And what I'm getting is y, the true data point, minus my prediction. So this part in the second half, everything after the minus sign before the square, is basically the prediction. That's the model. And our goal is to minimize, in this case, the distance between the y that I observe and the y that I predict. And that distance, as I've written it out, can either take on positive or negative values, and we don't really care if they're positive or negative. Right? We want to minimize how wrong it is whether or not I'm above the line or I'm below the line. So as I've sort of explained to you guys before, in statistics, sometimes the way we do that, the way we basically ignore the sign, is by squaring that. So if I'm above the line or below the line, it doesn't matter. Both get the same penalty. And by minimizing how wrong I am of the squared values of all of the points, I'm minimizing basically how wrong I am in a way that ignores the sign. Right? And I also want to sort of stress here, everything in this parentheses set after the y minus, so basically the xi b1 plus b0, that's the model. And you could imagine in data science that this model could be more complicated. It could be some function, that's basically right, that's my function of x, that's my linear function of x. You could imagine a quadratic function of x, you could imagine some more set complicated functions of x that has way more parameters, way more b values, and I can tune all those b values to try to, again, minimize the distance between the prediction of the model, x b1 plus b0, and the actual output I observe. And this basically is statistical learning. So though I have this formula here written in a simple way, written as a linear model, some linear function of x, actually this framework that I'm talking about, which is minimizing sort of how bad I am, how wrong I am, how noisy the model is, sort of works for any set of models. In fact, you might be familiar with the fact that you might be familiar with sort of machine learning and all it's done in the last 20 years, generated all this buzz from all these companies like Google and Facebook, et cetera, and part of the reason why that's happened is because we found really good ways to approximate this function f in a way that minimizes this error in a very effective way. And so basically what sort of the machine learning revolution, if you will, has done over the last decade is it's made this linear function be a much, much more general class of functions, and it's been able to sort of find these parameters of general classes of functions really well in such a way that minimizes this error effectively. But, said differently, all statistical learning sort of can be thought of in this framework. It can be thought of trying to minimize some sort of error here, in this case a squared error. And for the discussion today, this is sort of the form we're going to be focused on. Great. So with that in mind, I'm just going to say one more time, our goal is to minimize these epsilons, the noisy component, is to find the B1 and B0 that minimizes this epsilon given some sort of data that I observe, x and y. And again, in this case, I have n data points. N would be 4 here if that's not clear. Great. So that's exactly what I just said. In linear regression, our goal is to find parameters, B1 and B0, that minimize the residuals. Sometimes this is said differently. I don't think I've used this term yet. This can also be called least squares. That's called least squares because these values are squared. Again, that makes them all positive. It makes them symmetric, whether or not I'm above or below. And by minimizing these squares, I'm performing the process of what is known in the statistical literature as least squares. That is, I'm using this process of minimization, minimizing my error here to find my parameters, B1 and B0. Great. So I want to also just step through thinking about this probabilistic linear model one more way. And yeah, so here I have outlined the line, the linear fit, y equals b1x plus b0, mx plus b, if that's more comfortable for you. And let's say we've already learned this model based on some previous data, and I'm not showing it. So I have this best fit line. What can I sort of say about this probabilistic linear model as it sits? Well, I could say if I have some sort of inputs x or inputs y, one way of thinking about the outputs is that the outputs y have some average value. And so this is some new notation that you haven't seen yet in this class, and I want to get you guys familiar with this. What I have here on the left is mu y, then there's a line x2, that's again the leftmost character, and then there's mu y, there's a line x1, that's on the top and the bottom. And those refer to the mean values, and you can think of this vertical line as the word given. So the mean value of y given x2 is that top line, and the mean value of y given x1 is that bottom left character. And so that's just a notation, but it should totally make sense. Right? So by imagining some position x2, I have some prediction on average. That prediction on average is the mean value of y given that input x2. And how is that average value given? That average value is given by my linear model. Now, why is it the average value? It's the average value because the true data may deviate from that model according to some parameter epsilon. That parameter epsilon, again, is random. That parameter epsilon could be slightly above the line, or could push the data point slightly below the line. But in the limit of sort of infinite data points, or in sort of the way this model is characterizing the external world, the expectation is that basically that x value gives on average that y value over lots and lots of iterations of the data. And how wrong it tends to be, okay, wait, so here's what we say. So each outcome given an x has an expected, this is other terminology, I don't know if I've used that, but another way of saying the average value of something is its expected value, basically, what you expect over lots of iterations on average. So given some sort of input x, say x1 and x2, our model predicts some sort of average or expected value y in this linear model. Here's the thing, though. There's another component of the model, of course, the noise component, and that noise component describes how much a given output y will vary, how much it will tend to deviate from its predicted parts. Now you can see here I've got these bumps. We have not learned about this in class, but you've probably heard the terms before. These are bell curves or normal curves, or as well, I'll be using Gaussian curves. And they characterize sort of the structure of, there are some, I mean, they're used in a lot of applications. They're used all over statistics because of a number of things I'm not going to go into right now. But basically, you can think of this here as a way of characterizing the noise, epsilon, based on how much it tends to deviate from 0. So again, that Gaussian curve, which we'll go over more in class as sort of the semester goes on, but that Gaussian curve is a curve such that when the value is at a peak, or when the value is at sort of the rightmost side of the curve, I have a high probability of epsilon taking that value, and as I sort of move away, my probability of epsilon taking a value gets lower and lower. And sort of said differently, this Gaussian curve, its width is its standard deviation. So the wider it is, the more my epsilon tends to vary, the more my y tends to be either above or below its expected or average value. And the narrower it is, the closer my data, basically the skinnier that hump would be, the closer my data would be to a line. And the closer I would be able to predict a given output y given an input x. And we're not going to go through this, but you can actually imagine, given some data, I could also learn how wide those bumps are. And this would be sort of a different type of modeling. I would be learning not just parameters b1 and b0, but I'd also be learning, say, the amplitude of the epsilon noise. Great. So that was sort of structurally and conceptually what we're doing today. And it was all sort of in a framework that's quite simple, and it only used one dimension, only used one kind of input. And what we only thought about, like, say, predicting heights from weights or something quite simple like that. But of course, this model can be extended to a much more general case, and often is. And in that case, we don't have one input. We don't have one, say, height to predict some weight. Instead, we might have a lot of inputs to predict something. So you might imagine, if I'm doing some complicated modeling and I have a whole lot of data and I'm describing, users in some sort of application, and I've got a bunch of features about them. I have their age, I have their weight, I have their height, I have, a bunch of continuous variables to describe them. I might want to model or predict some other feature. And I can use all of those data I have to sort of try to predict that feature. Or thinking of a neuroscience example, you can imagine I'm trying to predict the movement of a monkey. Say the monkey, like the example we went through 2 weeks ago in class. The monkey moves his arm in sort of one of 8 directions. You can imagine I could predict that movement. That would be my output y as a function of the firing rates of not just one neuron but 100 neurons. And so you can actually think about this problem or this type of model in a framework that actually captures that exact thing, where I'm predicting one output, in this case y, and just so you know, for the purposes of this course, we're only going to be thinking about single outputs, single scalar value outputs. But of course, the input can be much more complicated. Maybe I take data from lots of different sources to predict the scalar output. I should say many of the results we talk about here today can apply to a multidimensional output as well, right? So maybe I'm predicting 2 things from the firing rate of 100 neurons, or maybe I'm predicting the firing rate of 10 neurons from the firing rate of 100 other neurons, right? All of that type of learning can be considered in sort of the linear regression framework, and really all it amounts to is, instead of learning just an m and a b from mx plus b, or a b1 and a b0 from the previous slides, I might be learning more parameters. I might be learning a b1, a b2, and as you can see here, b1, b2, all the way to bn. So so basically the number of things I need to predict, say some sort of output y, each one of those regressors is going to have some parameter b, and I'm going to have to learn that parameter b to try to, again, best predict the output y. And because these are all these parameters multiplied by those inputs x, and it's just that simple relationship, the parameter times one feature x, the second parameter b2 times another feature x2, etc., moving forward, that is the linear framework. That is sort of the linear algebra framework we've been working with for the last few months. And so this is still this would be an n-dimensional linear model. And of course, now that you're familiar with sort of linear algebra notation, we can write this differently. We can actually write this in a way where I think of this is just a dot product between 2 vectors, Right, so the vector x is of length n, it has n dimensions to it, it's n features of my data, it's, say, n firing rates of my neurons, and my vector b is a parameter of that model associated with each one of these features. So I also want to say, in the code that I'll be going through sort of at the end of this discussion, b here is actually going to include b naught. So you can imagine, sorry, I wrote this on the board when we were in class, but I know I don't have the convenience of a board right now. But you can imagine here, instead of writing b dot x plus b naught, I could reframe this equation, and I could just say b dot x, as long as x contained a 1 appended to the end, and b contained a b naught appended to the end. Does that make sense? So like, I take some vector b, and it's b1, b2, all the way to bn, and then I add b naught, and that's my vector b. And then I have x, it's x1, x2, all the way to the end, and then I add 1. And if I take the dot product of those two vectors together, I would actually include that b naught on the end, and y would just be equal to the dot product of b dot x, and I wouldn't need to include that b naught. I do that in the code. If that's confusing, take a look at the code. We'll look at it at the end. But I do that in the code because it's actually just a simpler and more concise way to think about the vector b and the vector x, but it's exactly the same model. So I'll say it one more time. We can think of, I have here written on the bottom, b dot x plus b naught. I could instead rewrite that as just b dot x, as long as I append a b naught to b and a 1 to x. And if I do that, the dot product b dot x is still that long equation at the top half of the slide. And that's the way I do it in the code, in case you get confused when you look at the code. Great. So now we're going to sort of conceptually go over everything I've talked about, but now using the sophisticated language that I've introduced you to, and I'm thinking about this in the n-dimensional case. But conceptually, it's the same as finding the best fit line that you probably did in high school. So the idea here being, say you observed k data points, so k observations of this input x, and you observed k outputs y. Okay? So the goal of linear regression will be to seek a line. In this case, it's not necessarily a line because we're in a lot of dimensions. So if it was like 2 or 3 dimensions, you could think of that as a plane. Typically, the terminology we might use is a hyperplane. That's basically an n-dimensional line. But it basically means that along each axis we have a linear relationship, but sort of visualizing that in the abstract is of course impossible. So the term as statisticians we might use could be hyperplane. So we basically seek a line or a plane or a hyperplane that can best predict y from my input vector x, which could be all of my firing rates of all of my neurons, as well as possible. Right? That's the goal. And I do that by, of course, learning parameters b, and the model looks either like y is equal to b dot x plus epsilon, or it looks like y is approximately equal to b dot x. So again, here on the right, I basically have the model with the noise component, with the random deviations I'm expected to get for any given data point. And on the left here, I don't have that. So basically, in that case, we're just going to say y is approximately equal to that dot product. That is, that output y is only closely related to the input x by a linear relationship. But if I have the noise component, we can make the claim that y is exactly equal, so long as epsilon here is this random variable. I know it's this is kind of probably a new concept, but it's this random variable that can sort of take on some sort of random value for every given data point x. And the goal here is to, of course, minimize the width, minimize the standard deviation of that epsilon, and maximize the predictive power, or how accurate output y is given some input x by manipulating those b's. So the b's that do that best. So this is what I've just said. We want to find the weights b that minimize this squared prediction error epsilon squared. So that minimize basically that epsilon, and in such a way where we don't care about the sign. So minimizing the squared value of that epsilon. Great. So now we need to think about how we actually do that. I've talked to you so far about what these linear models are and how they relate to these parameters b, and how our goal of tuning the parameters b is to best predict our outputs from an input, but I want to sort of step through how we actually go about finding the b. And this is sort of an important concept in statistics in general. How you go about finding parameters of your model via the minimization of say, some sort of error, in this case, the squared prediction error, epsilon naught. And, before I sort of step in how to do that, I want you guys to think back to your calculus class. And probably in calculus, you learned how to minimize or maximize a function. I wonder if you remember how you did that in calculus class, because probably what you were taught to minimize or maximize a function was to say you had some function as a function of x, and I wanted to find where it was at a minimum or a maximum. The thing I do in calculus class would be to take that derivative of x and set it equal to 0, and then solve for x. What does that give you? That gives you the minimum or maximum of x. And actually, we're going to do the same thing here. And in fact, this is largely how a lot of statistics works. In fact, a lot of statistical learning, maybe you can say all statistical learning, is in some ways finding where the derivative of the thing you're seeking to minimize is equal to 0. And there's a lot of effort that's sort of gone into this in different ways. Different complicated algorithms can basically find this special point where that derivative is equal to 0. But that's basically the overarching goal here. And because we have learned now linear algebra techniques in the last few weeks, we can sort of go through and figure out how to find where the derivative of the function that we're seeking to minimize with respect to our parameters equals 0. And we can find where that is, and then we have a solution to our linear model. And then we can just basically use the data to get those parameters out once we've found what the weights should be to minimize that model. And if that doesn't make sense, we're going to go through that in the next couple slides. So this is the thing we're seeking to minimize, right? We're seeking to minimize the epsilon squared. The epsilon squared is the outputs y minus the predictions of what those outputs should be. That's sort of the error. This is the squared prediction error, or it's this epsilon, this noisy component. So we can actually, again, said differently, our goal is to minimize this term on the bottom right. And how do we do that? Well, we take the derivative of that term with respect to b, and we set it equal to 0. You can see here what are the things that are the relationships here. I have y in this equation, I have x in this equation, and I have b in this equation. So if I take the derivative of that bottom right term and I set it equal to 0, I can solve b and make it just a function of my data. This is a really powerful thing. So that means you can give me some data, and if I have this special formula that b is some function of my data that minimizes that error, I can give you back the parameters that best describe y from x in this linear model framework. We should also say here that this n at this bottom equation should not be n, but should be k, or we can think of maybe k on top being n, so maybe there are n data points, but there's an inconsistency there, so don't let that confuse you. Great, so how do we go about actually doing this? We set the derivative of this guy equal to 0. Set the derivative of this bottom right term with respect to b equal to 0. We solve for b as a function of x and y, and that's what I'm going to do in the next few slides. And this is going to be a little bit linear algebra heavy, so if I'm going through this too quickly, I actually don't want you to think, I don't want you to worry about it too much. Basically, you can sort of step through this on your own in your spare time if you're curious, and also I don't want the derivation to be the thing that throws you off, because the real important concept is to how we're minimizing this, because that's sort of the fundamental point of this entire procedure, is minimizing this function, sort of how you do it. If you don't follow every step of the algebra, that's okay, but if you can see where we're coming from at the beginning and what we get at the end and why we get that at the end, that's sort of the important pieces. Great, so this is what I just said. We take the derivative of this thing we want to minimize with respect to b, and we set it equal to 0. And now I'm just going to put together all our data into some new matrices in linear algebra notation that will make this conquerable. So we can imagine here y, which, as I've said for today, we're just going to think of as some set of scalars, some single output. And I'm going to stack that up into a column vector. And then, of course, here x's, these x's can be n-dimensional, so this is going to be some big matrix of x, where I, again, record, let's say, n data points. And so I have n x's predicting n y's, and x here is some high-dimensional x, and I'm stacking this together in a vector. I showed you guys the notation for this a few weeks ago, but basically, when I take, if I want to think about this notation in linear algebra with these two bars on the outside, you can think of that as denoting the length of the vector, which is basically the square root of everything inside that thing squared. So what's taking the square root of everything inside that thing squared? What's taking the square of that? It's basically getting rid of the square root. So it's everything inside that squared. Does that make sense? So it's the same, oops, sorry. It's the same as this, right? That's all of those data points added up squared. And I've just written that out differently in this formula. That's what those double bars mean. Now, why did I write it out differently in this formula? Because if you write it out in this way, you can actually show, well, you can see kind of clearly that you can actually expand this into a representation of this matrix transpose times this matrix. If this step is confusing to you, you can just step through a particular example. Imagine some two-dimensional x and some, 2 data points or something. You could sort of see how if I take all of those terms, 2 data points, and I add the square of them up, I'm doing the same thing, in fact, as decomposing this two matrix representation into a thing times its thing transpose. And again, why am I doing this? I'm doing this so you can see where we get how we go from taking the derivative of something with respect to b, setting it equal to 0, and trying to find a solution using sort of this linear algebra notation. Great, so first we expand the term of this error term, right? And I expand it with this thing times this thing transpose, and then I just do FOIL, right? So I'm just going to multiply this first set of parentheses by the second set of parentheses. So what this is y transpose y minus some y transpose xb minus some xb transpose y. And then, of course, these final 2 terms are now added because it's minus times a minus, and that's going to be xb transpose xb. You guys should be pretty comfortable with that step. And I think I told you guys this trick last time. If I take the transpose of 2 things multiplied together, you can imagine reversing. This is the same as reversing the 2 terms and taking the transpose of each one, and that's all I've done in this 3rd step. Great. So now I want you guys to think about 2 really, really, really simple calculus rules that you learned before in calculus class. Over the course of the next couple weeks, you're actually going to get a little bit more in-depth of a calculus refresher, but you shouldn't need it too much to actually understand this derivation, because you only need the 2 most basic derivative rules you ever learned, right? Basically, well, I guess 3. The derivative of a constant of something, which, if we recall, is the derivative of a constant. So if I have, the derivative of a with respect to x, that derivative is 0. So what's the derivative of this first term with respect to b? Well, we know it's 0 because there's no b in that term. The next thing, the derivative of something times b, if I'm taking that derivative with respect to b, if I take something times x, the derivative of that with respect to x, I just get 1 back, so it just becomes that constant out in front. Right, so when I was in class, I wrote these on the board. I don't want this part to confuse you, but basically what I'm saying is if I have some derivative c times x and I take d dx of that, I just get c back. So in this case, the second 2 terms, I have the derivative of something times b and the derivative of b times something. So if I take the derivative of those middle 2 terms with respect to b, I actually just drop the b. The same way in not linear algebra notation, if I had the derivative of something times b, and they were all just constants, I would just drop the b if I was taking the derivative with respect to b. And that's what we're doing. And the last rule I need to give you guys is this final term, and this is something that you just have to sort of trust me on, but you remember in calculus, so I took the derivative of something squared. What I ended up doing was taking down the value of 2 and then dropping the square down to just to the 1 power. So, right, the derivative of x squared was like 2x, right? We remember that from calculus class. In this case, the linear algebra analog of a squared value is that value transposed times some internal thing times that value. So you can think of this final term as equivalent to taking the derivative of b squared. Right, taking the derivative of b squared here would give me a 2b. So that's actually all we're doing. That's all the steps here that we need to sort of solve this. and it basically just means that I'm going to drop this first term. These next two terms are going to lose the b, and this final term is going to keep one b, but there's going to be a 2 out in front because it's the analog of doing a derivative with respect to b squared. So it'd be 2b. Okay, so let's do this again. We take this derivative with respect to b instead of equal to 0. We're going to do everything I just said, and this is everything I just said. There's the term out in front. I dropped that first term because it didn't depend on b, and I took the derivative. That derivative is going to give me y transpose x minus x transpose y plus 2b x transpose x. Great, and that's equal to 0. And I'm just going to move that second term over. Okay? There's one other little trick we need for this derivation, and that's basically the fact that if these two terms on the left, this bottom equation, this y transpose x minus x transpose y, those terms on the left can actually be combined. And they can be combined if y is a set of scalars. And if that part's confusing, actually don't worry about it. You can actually just see by writing it out that if y is a set of scalars, you get some column vector minus some row vector, and you actually can combine those two. And so we can combine those. You maybe just trust me on that, or you can go through this by hand. But if we can combine those, we get the following relationship. Right, if I can combine those, there's two of them. So they both have minus signs, so it's minus 2 times a thing, and then equals minus 2 times a thing. I drop the minus 2's because they're on either side of the equal sign, and then I have the following relationship shown at the bottom of the screen. And then what do I have? I can pretty easily solve for b, and all that amounts to is multiplying by x transpose x inverse. So we remember that if we multiply a matrix times a matrix inverse, we get the identity back. That's equivalent to 1. Right? So if I multiply the left and the right side of this by x transpose x inverse, the right side becomes just b, or b times the identity, and the left side becomes x transpose x inverse x transpose y. Right? And there's the gold. That's the whole point of this lecture. We get a solution for b as a function of the data. X transpose X inverse X transpose Y. That is the solution to the weights or the parameters of any linear, of all probabilistic linear modeling. So this is a very powerful result. I don't want to understate this. If you give me some data X and some data Y, in fact, I showed you here only this for a single scalar X, but actually this, for reasons I'm not going through, this holds for n-dimensional Y as well. But if you give me any input data X and output data Y, I can just run this simple operation in whatever computer programming language I want, and I can give you back the parameters of the linear model that best describe the data, the parameters of the linear model that minimize the error, the parameters of the linear model that minimize the width of that random variable, right, that make X as close to Y as possible. So this is very effective. This is used all the time, all over the place. Companies, banking companies, finance companies, Google, Facebook. I mean, like, everybody uses this to some extent. Linear regression is incredibly powerful because of how simple it is, because this is so easy to calculate, and because it's such a fast solution to get this sort of quick relationship. So I hope that makes sense. I'm going to show you an example of this. This was a little bit faster than when I did this in class, and that's totally okay. I hope it's been concise. If anything was a little bit unclear, feel free to talk to me. But basically, this is sort of the whole overview of the lecture, and I'm going to go through examples of this in code. So let's look at some example code I have now. Okay, so here is the code that I think I've provided on the wiki, so you guys can download this code without too much trouble. I'm running this code. So this first part is just setting up things. In this part, I'm actually generating some data. I don't want you guys to worry about that too much. Let's just look at the data when I plot it. So hopefully this won't take too long. Sometimes Julia takes a while. Great. So there's the plot of the data that we are wishing to find a line to fit. So let's take a look at this as closely as possible. So again, here's some data, some input x, input y, and our goal is to find this parameter. These parameters, in this case, is two-dimensional, so this is just mx plus b, right? But the result I derived for you on those slides was for any dimensional, so it also works for, sorry, one-dimensional, some offset, but it's two parameters, right? Two parameters, but one-dimensional, so this b1 and this b0, but the formula I provided works for any number of dimensions, so I can actually use that formula. So what am I doing here? Well, first I'm actually describing that intercept, that b0, and I'm basically making some data. So this is what I talked about earlier when I talked about taking the dot product of b with x. I've basically appended some ones here. So this cat function is taking my data x, which is these points right here along the x-axis, these values, and adding to them a vector of ones as well, right? So you can actually see here, this is 50 by 2. I have 50 data points, and then I have just those x's, those data points themselves, and then I have 50 ones. And why do I do that? That's so when I take the dot product, I have some parameter that's associated with my b1 and some parameter that's associated with my b0, right? And I append that into some big matrix x. So just to be clear, that big matrix x is this guy. Right here. And why did I append the ones? In case you're clear, I was talking about it on this slide. Basically, if I didn't append the ones, b would have just been 50, sorry, x would have just been 50 single data points, because I have one-dimensional input, one-dimensional output, but I appended a 1 to it, so now it's the data point plus data point comma 1, second data point comma 1, second data point comma 1. That way, when I take the dot product of that with b, I can actually write y equals just b dot x. Right, so that's what I've done here, and that's going to be my x matrix, the data points and then ones, and that will actually, then when I learn the parameters, I'm going to be learning the b1 and the b0 all in one framework. I hope that is clear. Yeah, so that's what I've done. I've sort of added those ones to the x. And now I can actually use Julia here to calculate this thing right here. Right, so what am I calculating? I've called my x here is called full x. I'm taking transpose x times x. So, and then I'm taking the inverse of that. So that's, again, exactly the same as this equation. X transpose x, the inverse of that, times x transpose y. That's going to give me my parameters b. And because I added this one, b is going to be two-dimensional. So let's make sure that makes sense. Parameters here, two-dimensional, right? One of these is the offset, one of these is the slope, and the one that is the offset is the one that's corresponding to the ones that I've appended to the matrix, right? So yeah, this full x is my data points and my ones, and then so as a result, I get two-dimensional output, which is going to be b1 and b0, or exactly what I have shown here. b1 and b0, because this is one-dimensional, this is one-dimensional in my example. Great, so let's just plot that. So I can create a line, which is some, just set of x values going from, say, -4 to 4, and then I plot that as my value plus what I'm predicting is the output. What am I predicting as the output? I'm predicting the first parameter times my data plus the second parameter. So that's exactly what I have here. First parameter times my input x plus the second parameter. Sorry, here it's not the data, it's just abstract values of x, any value of x, right? Not a given value of x, but I'm looking at what that model predicts my answer should be. If I plot that, as you can see, I get my best fit line. Right, so maybe when you did this in high school, you had some sort of special formulas, or, I don't know, somebody gave you your m and your b, or you plugged it into Excel or something, and it spit back out an m and a b. Here now, you understand exactly where this is coming from. You've minimized the distances between these points and this line. All of those little epsilons. You found the special line that minimized all these little epsilons, and that line had these two parameters, b1 and b0, that I found here, and I found it using this formula, which was found by setting the derivative of that error with respect to 0. That's the whole point of linear regression. That's the meat of this entire lecture. If you guys follow that, which I hope you've done on this video, because it's been a little tricky to just sort of talk to a screen to do it, but I hope it's been clear, that's sort of been the whole point of the lecture. I showed one more thing here at the bottom because I did a two-dimensional example. Unfortunately, despite my best efforts, Julia plotted this not really well. I couldn't actually figure out a great way to do it. But basically, I wanted to show a higher dimensional example just to demonstrate that this technique's obviously powerful, not just with one regressor, one-dimensional regressor X, or one regressor X, one input X. And I really wanted to show that because typically this isn't done with one input, right? If I'm doing this for some sophisticated way, I've got maybe 100 inputs or 1,000 inputs or 1,000,000 inputs or whatever, and I'm using the linear model in a much more general way. So I just wanted to show a two-dimensional example. So in this case, I'm plotting some data with. Now it's going to have three parameters. It's going to have a b1, a b2, and a b0. So some intercept on this y-axis, and then some slopes corresponding to these two other axes. And actually, you can solve this using the exact same technique. So, I do the same thing. I append the ones to this matrix so I can learn b2, b1, and b0. And then I just solve for these parameters. These parameters now have three values, right? And I can now imagine plotting here. This would be sort of a hyperplane. You can think of, it wouldn't be a hyperplane, it would just be a plane floating in space, and that plane would minimize the vertical distance here. Those would be the epsilons, how far off I am and why. Those would be the epsilons of that. You can imagine a piece of paper floating in the space that sort of minimizes the distance to those data points in blue. Right, unfortunately the plot here doesn't look this good, but you'll get the idea. Is it going to go? Yeah, so it kind of looks like this. Yeah, it basically looks like a rectangle, like just overlaying this. But you can imagine here that like instead this sort of actually goes into the three-dimensional thing. You can't see it very well, but I hope you guys get the idea. Yeah, so that was the whole lecture on linear algebra. I hope that was clear. I hope this worked. I'm sorry for sort of dropping the ball in the recording during lecture, but yeah, hopefully this was useful for any of you guys who went to SFN. I hope you had fun, yeah, I hope you followed this. If you didn't follow this, feel free to send me an email if parts of this were unclear. But at least now you can go through these lecture slides and have a little bit of guidance, and you can even move around this recording a little bit to just see as I'm talking about each of these slides. Maybe hopefully you'll have a little bit of guidance as to how to interpret them. You just don't have to try to be left on your own to interpret this. And of course, come see me in my office whenever you want, if or shoot me an email and we can set up a time. If you want to go over some of these concepts, you're bound to run into them again in some capacity. I think linear regression is sort of ubiquitous. This process of like minimizing the least squares is also ubiquitous, and again this process of like taking the derivative of this guy with respect to some parameters and trying to find where it's equal to 0 is also ubiquitous. So you're going to run into it again and again in statistical science. So you're not explicitly going to be tested, at least in the next week, on this material. This isn't though this was part of the linear algebra module, this is not going to be on the module test at all, so don't worry about that. But these concepts are going to come up again in this course, and they're almost certainly going to come up again in your data science or neuroscience or academic careers. So I hope, you guys can take that seriously. But great, that is that. Take care.